Thanks for listening to my talk. I'll be talking about end-to-end testing your backend in Rust. And this is basically showing you some patterns and techniques that I've learned to make your tests more productive. Short intro, I am Rafael, a freelance full-stack developer from Hamburg. I've been doing mostly Rust work the past 1 or 2 years. So in my work, I'm always looking for ways to create maintainable and well-working applications. And I think we can all agree that tests can play a big role in that. I also think that Rust actually provides a very productive environment for building maintainable software, while also keeping up the development velocity without investing too much time into that maintainability. So today I want to share some techniques I learned during my work to make that happen in Rust. In the recent years, as I've said, I've mainly been doing work in Rust, and that's also involved writing lots of tests. They can provide a huge boost to maintainability, reliability, and the experience of developers. But the Rust ecosystem for web development is pretty young still, and it can be hard to find resources sometimes on how to do some specific thing, how to do it properly, and it can be a little bit frustrating sometimes. So today I want to present some patterns that I found helpful for testing web backends specifically using end-to-end tests. What do I mean by end-to-end tests, and why do I like them? For this talk, I'm going to focus on REST APIs specifically. You might also call tests or end-to-end tests for REST APIs integration tests. I find that this can get a little confusing at times, but the definition that I am going to use is tests that completely test the whole system, the complete behavior from an outside perspective. For REST APIs, it means sending requests to the backend and inspecting the responses that come back. Advantages of this kind of testing are that, of course, it's close to production, and we can hope to catch more bugs this way. For example, errors in our SQL queries, routing configuration problems, or even unexpected changes in the interface, the HTTP interface to the outside world. They also make it more natural to verify the system from an actual user's perspective, which means that we hopefully can catch more critical bugs this way that really impact our users. Potential drawbacks of these kinds of tests are that they can quickly become the slowest part of your test suite, and they can also be quite obscure because you're using such a large system in your test. So it can be hard to pinpoint where failures occur exactly. Because of the complexity, they can also become unreliable, so that means you have some flakiness, you might call it, accidental failures in your CI, in local development, which can be frustrating as well. And also they can become quite hard to read and write, because they can become very large. So let's oversimplify these disadvantages a little and say we have two problems here. We have performance of tests and ergonomics, which is, for me, how the tests are usable from a development standpoint. So I want to show you how Rust enables us to tackle both of these problems effectively. We saw that when we tackle these, we can get end-to-end tests and make them more useful for us, but I have some more reasons to actually care for speed and ergonomics of tests. First, when developing locally, your feedback loop is something really important. The faster you can run the tests, the faster you get feedback about the code you wrote, which can really enhance productivity. And the CI that runs the tests, if it gets faster, you will get faster code review cycles, which means faster development velocity. With ergonomics, we can make the test authoring more productive, which means we can write more tests in fewer time, and we can make the tests more comprehensive, covering a larger part of our system. Not to mention, of course, that it's way more fun to work with tests that are actually nice to write and not frustrating. Ergonomics also can reduce the bugs we find, or reduce the bugs we implement in our tests, because they can clarify how a test works, what it's testing, and making the test easier to understand. So, with that in mind, to tackle these two things, speed and ergonomics, I'd like to present 3 topics. First, I'm going to talk about how you can manage database access in your tests. This can quickly slow down a test suite. We're going to look at ways to make it fast. We'll apply the build-up pattern in the second topic to encapsulate some common test code, making our tests way more short and easier to understand. And thirdly, we'll cover how to use a single code space or a single test code to cover similar features, multiple similar features. Let's start off with the database. Web backends often need something like a Postgres database, MySQL, maybe even a NoSQL database. This can quickly become a problem because they are basically an outside system and you cannot control them very easily from your test. So let's take a closer look at how we might approach this. Fundamentally, our problem is that we want different tests to write to the database, but not influence each other, of course. We want each test to have its own little world and its own little application. So to achieve that, here are some approaches that I've seen. We could just run each test one after another and make each test clean up after itself, leaving a clean database for the next tests. This is slower than it has to be. If we run multiple tests in parallel, we can achieve way faster test suite. Second approach is to mock the database. So we just put a little piece of code in there that's like imitating our database for a test-specific purpose. But this means that we don't actually see how our code interacts with a real database, so we catch less bugs. We could also carefully run all our tests in one database. Just don't do any cleanup, just be very careful, only insert random data, only query the rows that we have modified in that test, and try, when we fetch multiple lists of stuff, we try to ignore rows that come from other tests, or we try to filter the lists we fetch so we only get the data we want. This is pretty hard to do correctly. It's also pretty cumbersome. You need to be very careful, need to think about it a lot. The last point is using SQLite in-memory databases. Those are temporary databases that you can quickly create and destroy. It's a very elegant solution to our problem, but it only works with SQLite, and sometimes you just need Postgres, for example. So you see that these approaches all have their drawbacks. Let's look at 2 more approaches that avoid these. Our first approach, using database transactions. Some databases provide guarantees about transactions, meaning that different transactions are basically completely isolated from each other. So by wrapping each test in a single transaction for itself, we can guarantee that test only running inside that transaction, the application included, will not interfere with any other tests if all our tests do this. So in Rust, we could do this by injecting the transaction using a shared state mechanism that many web frameworks have, or another approach would be a from request trait, which you might know if you are familiar with Axum or ActiveX Web. And the advantages of these tests are that we are closer to production, of course. It's better than mocks because we catch more bugs, and also it's faster than sequential test execution. It's also pretty simple to implement. It's a commonly used approach. You will find articles on how to implement this online. The problem with this is that your database needs to provide you the guarantees around transactions that you need. Also, you will have to write your application in a way that allows you to create a separate application instance for each test you run. Sometimes that's no problem at all. Sometimes that can become a problem. A little surprisingly for my team, we found that we can also have problems with database logs with this approach, because some queries will obtain logs for rows or even whole tables, depending on what you do. And your transactions will run longer than for a usual request, because some tests might run up to 500 requests, I don't know, and the transaction will be open for all that time, meaning effectively it can cause your tests to slow down again. Lastly, because our application is running inside a transaction and the application code receives this transaction, the application code itself cannot really use transactions inside that other transaction. This is something that many databases do not support. You will have to use something like checkpoints to emulate nested transactions. Some ORMs support this, others don't. Can be hard to implement yourself. This is just something to keep in mind when using this. A second technique, cloning databases. This is a Postgres-specific feature that we can use to just copy one database completely to create a second identical database. And this is actually pretty fast. We can do this for each test and still get a considerable performance benefit. So by effectively cloning the database for each test and then configuring our test-specific application instance to use that cloned database, we can get complete isolation for each test without any transaction wrapping. We just drop the database after the test is done, and we're good. Advantages of this, of course, we don't use a mock again. We have no locking problems. We can just use rollbacks in our application code, can use transactions in our application code. This will be fine. It's pretty fast, of course. And with the caveat that it can become slow if your disk doesn't have the throughput required to create and destroy all these databases. So your disk write speed may become a bottleneck. Also, of course, you still need to be able to create an application instance for each test you run. Let's see, independently of these two approaches, how, if you decide to use a real database, how you can tune it a little to make it a little bit faster. This can also help, or I might say you really would want to use these two tricks to use the database cloning approach to reduce the dependency on your disk. So first thing you can do, you can run your database in a tempfs backed container. This means that your database won't be written to disks. They will be written into the working memory, which is way faster and doesn't, in my experience, this doesn't make such a difference if you have an NVMe SSD, for example, but if you have like a little bit of an older hard drive, this can make a huge difference. Also, you can switch off some durability features of your database. This is an example for Postgres. Switching off these three features will lead to problems if your database crashes, but this is something that's designed for the case of a power outage in the data center, right? If we just run our tests for a minute and the database crashes, we just run them again. That's fine. And it will speed up the application and the tests a lot. So with that covered, we have used the database cloning approach in a recent project to run about 2,000 tests in 30 seconds on a modern desktop PC. This does not include compile times, it's only the runtime. With this kind of speed, you can watch a subset of the tests for the specific feature you're developing, and it's almost instant. So this is a very sweet feedback loop when you're developing. I really enjoy that. I think everybody will enjoy that kind of speed. And we've seen how we can achieve this while still using a real database, which means that we can really be sure that a request that gets handled in a test will very probably be handled in the same way in production. With the database covered, let's go to the second topic. We can look now at some Rust code and see how we can make it a little bit more concise, easier to understand, and maintain. So, in a fictional dog registry application that we write using the Exum web framework, this is how we might define a dog using a struct written out here. It has a name and it has a primary key. And we now want to write a test that creates a struct like this through our REST API. So this is just the test wrapper, and we will now look at how the test contents might look. It's a little bit much, so we'll go through it step by step. First, we have this testing app. This is something we might define to create, for example, our custom database for our test or a custom transaction that wraps this using the approaches I just showed you. And using this app, we can now prepare some data, just some JSON data that we want to send. and use the app to actually dispatch a request to the backend. We see that we build a whole request here. We specify some settings. We say it should be a post request. It should go to the docs endpoint URL. We set the appropriate content type. We serialize the JSON we just created. And then we send it off using the router inside our abstract, which is a construct from Axum that basically represents our HTTP routing functionality where we can just dispatch the requests. Next, we check that our request succeeded. We check the status code, and we deserialize the body we received back from the backend into our doc struct. This checks that it has the correct shape that we want to receive in this test. And finally, we can check that the data contained in this struct is actually also what we expect it to be. This test example is pretty much directly taken from the official Axum documentation. And I think it's pretty good. Like we just went through it. I hope I was able to explain it well. And I think, nonetheless, we can optimize this a little. There are many conventions in a typical REST API that we can just assume when we write tests for a specific application. So we don't have to write out all this code explicitly for each test, I think. Let's see how we could write it in a different way. This is a snippet that does the exact same thing as the test I showed you before. It creates a new testing backend. It sends our data, deserializes the result into a doc struct, and asserts that the data we received matches our expectations. We do this by implementing a pattern that I call for this talk a request builder, a test request builder. This request builder knows the ins and outs of our application. It knows how it should behave, what kind of type of bodies it wants to receive, what kinds of bodies it returns. We can use this request builder to do common operations like create, read, update, and delete requests. We can also add application-specific methods for doing other things. Basically, this request builder provides a convenient interface to use our application from the outside. One example for how this simplifies our stuff is that in tests it's totally okay to just panic. So here we don't see any unwraps. This is all hidden inside our request builder. We just write out our happy path, how we expect the backend to behave, and if something doesn't, this will panic and create a test failure, just how we want it. The request builder also knows, by calling the app docs method right here, the request builder knows that we want this endpoint to return a doc struct. So it deserializes the response into the doc struct automatically. I've written a type annotation here, but this is optional. You can leave that away. So with that doc variable, it's now typed. We can conveniently access the struct fields and use it for assertions. How does this request builder work? This is a pattern, not a library. I want to emphasize that because this needs to be tailor-made for your application. You need to look at how your backend works, what the interaction looks like, what your API's shape is. And I will just show you a simple implementation that can get you started, which you can easily extend for different use cases and build upon. At the end of the talk, I'll link to a repository with example code with a little bit more of an extensive request builder implementation. So we see the test request struct here, which is the representation of our request builder. So this request struct contains all the information we need to dispatch a request to our application. It's the Axum router that we saw previously that accepts requests. It's a base URL for the endpoint we want to contact. And it's a phantom data field that we need to make this struct generic. Earlier when I told you that the request builder knows what kind of response it expects from the backend, this is the generic type we see here, the response type. This is the type that we expect it to return. And to use that in the struct description, we will have to add a phantom data field because we cannot just use a generic type without actually having a field without it. Without having a field with it, yes. So going on to construct this request builder. We implement a method on the testing abstract we saw earlier. We implement a method for each specific endpoint our application has, and this method configures our request builder for that endpoint. This is a pretty basic configuration. Of course, you can extend this to cover other use cases, other behaviors as well. But this is how it basically works. We can see that the URL to the docs endpoint is passed here, which is the specific part for this endpoint, as well as the dog type as a request, as a response type here. Implementing the request builder itself, the functionality. We just do that on the test request struct itself. Don't use any traits or anything. It has a generic parameter, our implementation. It's the response parameter that we already know. We have to put a trait bound on it here because we want to deserialize the type from the body we receive. The function that we want to implement here is the create function used to send a post request to create a new entry in the backend. This takes an input argument that's basically anything we can serialize to JSON. And it returns, of course, our response type. This is why we drag the type through all the previous lines of code to use it here. Then we use the same snippet we saw earlier in the test to dispatch a post request to our backend, serialize the body, and take the response out of it. We then check the response status, also similar to the test we saw at the start, and deserialize our body into the type we expect this function to return. Note that, let's go back a bit, right here we use the base URL from our configuration. So this is the endpoint specific configuration we have here. So that's not what I wanted to do. Let's see. Right. Let's look at some examples. We've seen the basic implementation. These are some examples for how we could extend that implementation or use an extended version of that implementation. So it provides the common operations you would want to do on a backend: create, read, update, delete. We could, for example, fetch a dog using its ID with a very simple API. Another example, if we expect our backend to return an error, we just add a new method called expectError, which we pass the status we expect to and send some invalid data, for example, and see that our backend responds with an error in a shape that we expect. So note that with the expectError, we can also override the response type we expect here. So suddenly we receive an error struct here, and we can read the message part from that struct and check that it's formatted as we want it to be. So the request builder's defaults normally allow us to focus on the parts that are interesting about our tests, right? But the request builder also gives us the flexibility to override these defaults. Of course, this is just all the advantages of the builder pattern. Another example is you could extend the request builder to add a query parameter method where you can send pagination options, for example, and then check that we get the correct list of results back from our backend. So I'm pretty amazed by how small this code is. You might ask me, Rafael, why do you show me this? This is just like, you're just refactoring code from one place to another. Like this is, we know that the request, like the builder pattern is great, you know? But I haven't seen this before, and I think this is a really great pattern, and I basically want to motivate you to try this yourself, because I think it's a really different experience, and it takes some effort at the start, so you just have to get over the little bump at the start to implement this, and then you will have a much nicer experience. And I think that sometimes people will just not want to put that much effort into their tests, and I'm going to say here that it's worth it. Because it makes the tests faster and easier to understand, faster to write. With that in mind, the request builder can be used to go one step further. We use it to write a test once and apply it to many endpoints in our application. First, let me introduce a crate that I really like. It's called EuroRust test. It allows us to do some neat things. In this example, we have added a validation mechanism to our API. So this allows us to send a request and check if it's a valid request without actually inserting anything. It's a fictional use case. In this case, we have added a validate method to our request builder to accommodate for this, and we have written a test to check that this validation works. If you look at this test, the shape is pretty similar to the other normal creation tests we had before. And since the code is so similar, we can now use the EuroRust test crate to combine these two tests into one. We do this using macro magic, of course. So we add the EuroRust test attribute, and we can now specify two cases. And EuroRust test will just duplicate the test code for us and inject these two values specified in the cases using a normal parameter. I think this is very nice. It's an intuitive way to parameterize the test. We can then use this parameter to pass it to our request builder to vary the test behavior depending on that parameter. So let's go now one step further. We can, instead of passing a Boolean as a case argument, we can now pass different endpoints of our application using the request builder. We just create different instances for different endpoints and can then, for example, check that the base URL configured in the request builders, which should also be the base URL you're using in your router configuration, that this is, in this example, versioned, for example, if you have a versioned API. So this is pretty cool. You could also, of course, dispatch requests. For example, you could check that the error codes your application returns for every endpoint are what you expect. You could check that you cannot send unauthorized requests. You can add fixtures to your request builder and see that the happy path tests just that the basic features of creating stuff and deleting stuff work. You could check that your pagination functionality works as you expect. All this can be made generic, so you write the test once and it applies to your whole application, as long as your application has a consistent interface, of course. I think that the request builder already provides some functionality to make your API consistent because it urges you to write your code in such a way or your interface in such a way that it works with this request builder. So this is good in and of itself. And these generic tests are a way to make that a little bit stricter. You might say that this is a little over-engineered. I'd argue, yes, it is, but it's also very fun. And I think having fun is a really important part to just pour in the energy to write the reliable software, to do it well, to write all the tests you need. And I hope I've whet your appetite a little to also do that in your code bases. As a conclusion, I want to highlight the three topics I talked about. We've looked at database access using transactions or database cloning to isolate tests using a database. We've seen a way, the request builder pattern, a way to make your tests more concise, to make your code shorter, faster to write, easier to read, more fun to write. And we've seen a way to apply this pattern to make your tests more efficient, even more efficient by applying them to many endpoints. With that, I'm Rafael. Feel free to chat me up after this talk. At the rest of the conference, I'll be walking around. You can find the example code on the GitHub link here. You can find the slides on my website, rafa.ee. And of course, you can contact me on Twitter. With that, thank you for listening.